Hello and welcome. Today is Thursday, April 30th, the last day of April. So we went through all of April online and we just have one more month, May, to deal with. And then it's all over. So welcome back. It's been a while actually with you guys. Haven't done a stream in a while. Actually, I felt like I oversaturated the market with our product, so it seemed like the value of our product diminished, and less people were inclined to come watch us, right? So maybe doing less of these streams might be better, and so so yeah. Uh, so of course, we are getting closer and closer to our AP test, and therefore we'll do even more small quizzes and stuff to continue to practice, make sure everyone is working as hard as possible and not taking their foot off the gas pedal yet. Physics had a stock market crash. Indeed, I'm actually looking at it. It went crazy yesterday, and now it's coming back in line. It's going down again. Similar to how your grades are, right? We had a quick boost. The federal government started buying up stocks, so that quick boost from your extra credit, and eventually, as we input more and more assignments, it should equilibrate. All right. So anyway, let's begin with a couple of things. Number one, the College Board should have sent you an email. So make sure you're always reading your email regarding the AP test. AP forms, please add onto your Canvas. Okay, so the College Board has been sending us lots of stuff. They should have sent you a link, this YouTube link, where you should be watching. Here, let me pull it up. Boom, there it is. You should get a link in your email, and there should be videos here. There's 5 videos. You should definitely watch at least the first 3, and it will explain how things are. So you have how things will be when you take your test, and then next week. I believe perhaps Monday, maybe Tuesday. I'm not sure which day. One of those 2 days. We will do a walkthrough of the system that they use. So we'll be able to do a beta test of their system. So watch, check your email for this link from College Board, or I don't know. I guess you can copy and paste it. There it is. And then you can watch all these videos. So that should be part of your assignment for the day, is to watch these videos. And so you're comfortable and you know all the stuff that you need going into taking the AP test, right? Okay. So let's begin with perhaps the no. I want to punish students who put things off. Check Canvas form 17. All right. So anyway, in the first quiz, that was last week. And in the first quiz, you had this very interesting problem with dynamics cards. The dynamics card, there were 2 dynamics cards. and then there are magnets in between, so there's magnetic repulsion. So similar to the cars that we have. What is interesting is that the track itself is not level; it was actually slanted. And so they were talking about this net external force on the system and all that stuff. So things that you should know going into the problem is that it is slanted. There's a magnetic repulsion. And of course gravity pulls it down and all that. So let's go through all this. It was only I made it only worth 7 points, and the points will increase as we do more and more quizzes. In part A, you have a graph, and the graph shows the momentum of both objects. So one of them starts off here at a positive and then it goes upwards. One of them starts here, let's see, this is a tick mark, this is a tick mark, and even though are they going to go in the test or assignment, everything is correct. I did not make any mistakes. So that should answer your question, Emma. And the second one is not directly halfway. It is actually slightly above halfway, and these are things that you are required to take note of. Right? Don't just because it's between 0 and the first tick mark doesn't mean it's halfway. Right? It's actually, one could argue, it's somewhere around 1/3 of the way, and of course it goes down. All right. So this is your momentum vector as a function of time. And the question was, based on the graph and the graph only, of course the cars started from rest. Cars start from rest. But the question is, based on the graph, do we start from rest, yes or no? Blah blah blah. And so then, even though you're supposed to start at 0, the graph does not show you that, right? Is there a way we could see the question and a response again? No. Actually, you can click. Oh, you can only see the total number that I gave you at the end. Yeah. You can only see the final score that I gave you at the end. But you can also see the comments. So I wrote down comments. I wrote down comments. So if you go to your Canvas, you can see comments. And so I put in comments for each section and why you missed it and all that. So you can read the comments. Anyway, based on the graph, all right, so T0 indicates the start of the graph, not necessarily the start of the experiment, right? So obviously this is no, and that's because there's a non-zero momentum at T0. Right, pretty simple. When you answer questions, make sure you start by establishing the claim. Okay, some of you are writing a bunch of stuff and going roundabout way, talking about all sorts of things. You want to be very clear and to the point. Okay, read the question and answer the question directly first, and then justify the question. Reason or justification. Okay, So be very clear, precise, concise, and get to your point. Right? So obviously, we know that the cars started from rest, but that's not what the graph is showing. Your t0 is showing you a point after the cars already started moving. If you have a non-zero velocity at t0, that means at 0 time it was already moving. Where did it start? Well, we can extrapolate the data by going backwards in time. Whoa, time traveling. And see where the lines intersect at 0. Like so. And so somewhere at negative time is when the cars actually started at 0 velocity. Right, so the graph starts off after the repulsion started happening. There's no real collision. You just, you're holding the cars down, I suppose, and then you allow them, when you let go, the magnetic force accelerates it. Of course, it's slanted, so that's kind of important too, and we'll come back to that. The slant applies a gravitational force. Part B says to find the net force, F net. Okay. Sorry, net external force. And a few of you kind of went off the track, off the rails. Haha, get it? It's off the rails. A few of you went off the rails and said, well, the net external force is from gravity, which is technically true. The outside force is the gravitational force. However, you said it is equal to mass times g. What in the what? Well, are the cars really accelerating at the rate of 9.8? The only time these cars would accelerate at 9.8 is if the cars were, free falling through the air. And that is definitely not, and that is not what's happening here. We are on a ramp. The ramp has a slant, so it's a ramp problem. And if you're going down a ramp at some angle, what is your acceleration? Chat, what is the acceleration of an object going down a ramp at angle theta? Ow. Just hurt. Close, bubble guy. Close. The question was not the force, but the acceleration. There you go. It's g sine theta. And so we know that the angle is very minimal, very minimal. It's only a tiny little slant. So here's our ramp. So imagine being like, 5 degrees or something. I don't know, something small. We don't actually know what the angle is, but we know that it's a small angle, and sine of anything less than 90 is definitely going to be less than 1, right? So this portion here, the sine of the theta, is a value that is less than 1. So the acceleration is definitely less than 1. But there's no way to calculate the acceleration this way, so you can't do it this way. So this is false. Actually, this part is true. It's just this part is false. It does not equal mg. The other thing that you have to note is that they are talking about the net external force on the system. On system. So both cars together. A couple of you found the slopes. So one method was to find slopes and add them. Or just use the impulse momentum theorem. Fat equals delta p. So impulse is equal to the force times the change in time. Or actually, this kind of leads us to the real Newton's second law, and that is force is dp dt, or the derivative of momentum. Well, we're going to stick to delta. Forget about derivatives. We like big fat Dorito chips, not the crumbs. And so you could do change in momentum, and this is the P final of the system minus P initial of the system divided by delta T. Okay, and when you do this, you have to make sure you look at the values carefully. Some of you are just using weird numbers or just made mistakes, and try to choose values of your trend line and make sure you try to accommodate as many points as possible, right? If you only choose points that are really close together near the middle or somewhere here, and you actually use data points directly, then that's not the best way to find the slope. Okay, we want to choose points that are further away, that encompass the entire data set. Okay, so across 10 seconds would be better than doing a slope over like 2 seconds or 4 seconds. Right? Or just look at the values. So your two values at t0 add them up to get momentum initial. So let me use pink. Pink here and pink here is pi, which is p1 plus p2 I. And then I'll use blue, so blue would be P final, which is P1 final plus P2 final. All right, then you do PF minus PI and then divided by time. Okay, some of you just drop the answer, which does not answer the question. The question is calculate. You'll get calculate or derive, or or it might be derived for you and you have to argue one way or the other. If you just dropped an answer, you got 0 points. First of all, it's fishy. It's very sus. Second of all, you have to be thorough. If you're going to derive or calculate, start with your general formula, indicate what you're doing, and then actually show what values you're using, etc. Don't just jump from the formula to an answer either. Be as thorough as possible when you answer these questions. All right, and then what was part 3? Part 3, yes. So this was worth 1. This was worth 1 if you said, oh no, what am I doing? Part A was worth 1 if you said no and you justified it correctly. Part B was worth 4 points. If you have the equations, you showed how you found it, what values you're using, and the actual value with proper units, newtons, etc. And in part C, get 3. Part C, whoa. Part C is a weird question. It was only worth 2 points. We know that the masses of each of the carts are, what was it, 5 and 1 kg? So 5 kg and 1 kg. All right, and the question was, if the masses were changed, 2 and 4, does it change the net force? or does it change, your answer from part B? And the answer is no, because the mass of the system didn't change. Mass of the system is still 6. Simply as that. Right? Now, why does that happen? Well, the change in momentum per time would also have to equal the net external force would also have to equal the mass of the system times the acceleration of the system. Right? And we know what the acceleration, the acceleration of the system is, right? It's still g sine theta. The g sine theta certainly didn't change. And since the mass of the system didn't change, and obviously ISBO, F net is the same. F net is the same. All right. So what have we learned? If we're going down a ramp, we are certainly not accelerating at g. It's definitely slower. It's definitely slower. Impulse momentum theorem, very important. Fat equals delta p. Or change in momentum per time is the net external force. Now, notice how in this form, if pi equals pf, so if momentum is the same and momentum is conserved, then f equals 0, right? See how that works? Notice how, of course, this is working backwards. We know that momentum is only conserved if the net external force is 0. Okay, so the fact that it is not conserved tells you that there is a net external force. Alrighty then. Any questions from the chat? So again, A was worth 1 point with proper justification. B is worth 4 points, and then C was worth 2 points. The second quiz is a little too easy, if you ask me. Where you're pushing 2 blocks. That was yesterday. No, not yesterday. When did you take your quiz? Tuesday. Let me label them 1 and 2. I don't remember. Let me pull it up. Yeah, this is right. 1 and 2, and you're applying a force F. You're applying a force F. There's no friction, so you're definitely accelerating. All right. A couple of things that I should mention. Probably the small minor details. For example, labeling forces. Let's do some FPDs. We'll do 2 of them, one for mass 1, one for mass 2. Of course, we have gravity, M1G, or you could also call it FG1, force of gravity 1. And of course, we have normal force, Fn. Don't just call it Fn, because you're going to have another Fn on the other end. Call it Fn1. Now, I didn't draw the arrows correctly. Yeah, it's so, well, I'm going to go into a little bit more in depth with this question. Obviously, your quiz was much more general, so let's see how what are the different styles of questions the College Board could throw. Number 1 is grids and vector lengths. Perhaps we might have to analyze an FBD and talk about what is wrong with all the FBDs. So one of the things that I did wrong is that these two, the Fn vector and the mg vector, these two should be the same length. Remember, the length of the vector indicates the magnitude of the vector, and since we're not going to accelerate in the y-axis, they're definitely equal. Okay, how should I draw the force? Well, there's only there's a force pushing, the applied force is F in this case, is pushing Fm1 to the right. Okay, I don't know what the magnitude of that is, so I'll just draw a generic arrow. Okay, all right, now question. I did not give you an FPD question. What you could do is you can type it out, like you can type the FPD out in words. Some people did it in their response. So you label your forces and then indicate which way they're pointing. All right, chat. Is this it, or am I missing something? Ooh. Remember, this is mass 1. Is this it? Remember, mass 1 is the one that's being pushed. Based on the fact that I'm asking, the answer is probably no. Fn. Yeah, so there's a pushback, and we need to label it. This is the interaction that is happening here at this interface between the two boxes. Yeah, and how should I draw the arrow? How should I draw the arrow? We know that it's pointing to the left, but is it bigger than F? Is it the same size as F? Or is it smaller than F? Yes, it's smaller than F. Why is it smaller than F? This is F. And just so you remember the notation, I know one person who did the notation backwards. Smaller because it's accelerating to the right. Yeah, it's accelerating to the right. F is winning. The pushback is smaller, of course, and the notation is on by. So the first number is the object that it's on, and then the second one is the force by. So this force is on object 1 by object 2. So F on 1 by 2. F1, 2. On by. Yep, one person did it backwards. I'm not going to tell you who. Let's go and finish off the other one. So of course we have M2G. Okay. Oh. This is Fn2. Notice how we have to label the Fn's different because the normal forces are different on each object. Can we just write Fn2 on? Yikes, that is not elegant at all. So use the proper scheme. But theoretically, if you explain everything that you do, the grader is unlikely to take off points, as long as it makes sense, of course. All right, chat. How should we do this differently for object 2? I know we have Fn2. Now F the applied force is not directly on object 2. There is a force from object 1, definitely, and that force is equal in magnitude but opposite in direction. That's why I'm using blue here. This would be the force on 2 by 1. On 2 by 1. And we have to make sure that they're the same. There is still something wrong, or maybe, it's wrong because I didn't state it yet. So what else? What other minor detail did I not go over, or what is something else that is important to distinguish between the two FPDs that I did not do yet? What else is important to differentiate these two FPDs? Again, the size of the arrows for FN energy. Yeah, M1G is smaller and M2G is bigger. So these arrows, these vertical arrows, should be longer. Oh no. There we go. There we go. All right. So not only are they bigger than F1 and M1G, but they are still equal in size to each other because they're because there's no vertical force here. Now, if I press down, if I were to push downwards, okay, and I have an applied force with a y component, this y component of the applied force would increase my normal force, right? So that then it would be different. At that point, it would be different. And the two vectors that would point downwards, the y component of the applied force and M2G, would have to equal the magnitude of the upward normal force. All right. Yeah. So part A says derive the magnitude of the acceleration, and you can do some sigma equations, solve for acceleration. Of course, we can just stick to the x. Force minus F12 equals M1A. F21 equals M2A. When you write your equations, remember the right side of the equation is just the singular mass. This is sigma Fx2. This is Fx1. So that's why we used mass 2. However, the acceleration of the system is the same acceleration for each individual blocks because the blocks will be moving together. Blocks would be moving together. Then it's just a substitution. We know that the magnitudes of F21 is equal to F12. And then we can do a direct substitution and solve. Oh look, it's sigma F over sigma M. Yeah. Don't just use the shortcut method. Shortcut method was great if there was MC, but this year there's no MC. We called it the net force on the system. And the denominator is not necessarily net mass. We call it the mass contribution. Remember, this is just a term we just made up in our class, but it makes sense. And so, of course, for linear systems, the mass contribution is m, and for rotational systems, the mass contribution is I over r squared, where r is the radial arm. Yes, if it says derive, you have to show all steps. So what steps should you show? You should show boom, you should show boom, or at least state. You can state it. Now you should show the substitutions. You don't have to show moving variables around. Once you show the substitution, you can go directly to the answer. So moving things around, factoring, isolate, like all that is not necessary. Yeah. All right. So with 3 blocks, of course, this is basically like the pulley problem we had on our test. Block 3 is now added to the system. Here's block 1. Here's block 2. I should have just used ink to shape. Why didn't I do that? Ink to shape. Block 3. Oh, I don't like that. Go closer. There we go. Block 2. I mean, we're adding mass to our system. The inertial contribution has changed, blah, blah, blah. So you can talk about how you could do it. And, do all the sigma stuff, get to A. Now technically, in part B, it doesn't say derive. It doesn't say, whoa, ink to shape. It doesn't say derive. It just says indicate. So you could shortcut. Now you don't have to shortcut. You can go the long way. The safe bet is always to do everything, show everything. So use your time. Use all the time that is given to you. Right? If you have 15 minutes, use up those 15 minutes. Some of you are trying to do this in like 6 minutes, 8 minutes. No bueno. Yeah. All right. So it says indicate whether the magnitude of acceleration of block 2 is now larger, blah, 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 and then justify. You can say that the mass of the system is increased, or the system has more inertia. Always use the word inertia. It's our favorite in AP Physics 1. The system now has more inertia, therefore the acceleration will go down. Or just derive this formula, play it safe to get maximum credit. All right. Yeah, that quiz was kind of a freebie to balance out quiz 1. You will have a quiz tomorrow, which is May 1st. This one will be a little bit more challenging. It will be challenging because it'll be different. It'll be different. Very interesting. Very interesting. Now you know that the College Board has windows for their tests, and of course we will have a window for our final exam, which is during finals day. And so the window that I have currently is a little too big, and therefore I will start I'll start shrinking the window of when the quiz is open, so it's closer towards what it will be like. For the final, it'll be like a 4-hour window. But the test is not 4 hours, obviously. It's like 45 minutes or something. There'll be two different parts to it, so we'll talk about the final after the AP test. Our full focus should be on the AP test. Anyway, expect the windows to be shorter and shorter after the AP test. So after the AP test, we'll start messing around with timings. All right. I suppose that is all. Do we have homework? Yeah, we do. What's due tomorrow, chat? It's Friday. Every Friday is like something due, right? Is it 3 and 4? 3 and 4, yeah. My AP units 3 and unit 4 MCQ. MCQ? No, you guys are not 11:45, are you? You guys are. Oh, the my AP. Are you really gonna wait for the actual deadline? I'm gonna tell you right now. There's gonna be some sort of server maintenance or something. It's gonna crash, so don't wait. Don't wait. But technically, yes, you are correct. You want to know for sure? Yeah, you're asking for a friend. Asking for a friend. Saturday? No, it is not Saturday. It is before Saturday. Nope. Not only is it 15 minutes less, but typically they go under maintenance and stuff, so you're probably not going to have the end time. So if you think you're going to plan it to do it Friday night, you're going to run into issues. Literally do it right now, so you don't have to worry about it. Okay, so tomorrow we'll take a quiz. Monday, I will start doing some of those FRQs. So take a look at those over the weekend. We'll go over some of those FRQs, and we'll also do like a simulation of the College Board platform for the AP test, and then we'll do some more quizzes. So be prepared. Thanks for tuning in. I'll see you next time.